Hi everyone. In this video we're going to be discussing how to work with the comparison test and limit comparison test. Now the reason why we even have a comparison test is sometimes we're going to be given series where it's a little bit difficult to determine whether or not it converges or diverges right away. And what we're going to do is we're going to compare it to something that we're already used to. Something as maybe a geometric or a p-series. And if we already know that that p-series or geometric series or something like that converges or diverges, then our original series is going to converge and diverge just based off that theory. Now suppose you're given a series. We're going to compare it to something that looks just like it. Now both of these have to be positive terms. And if our first original series is less than what we're comparing it to, and B of n converges, then A of n also is going to converge. And the theory behind that is this. Let's pretend that we have a list of A of n terms. But then we compare it to something that is always going to be greater than it no matter what, all the way to infinity. Well, because of that theory, if B of n, if we make it converge, that means that A of n is forced to converge as well because it's always going to be less than B of n, so it's going to converge to some number. Now, in the case where we have an A of n and it's less than B of n, but we get B of n to diverge, that's not going to tell us anything. And because of that, that's why we're going to have to use the limit comparison test, which we'll learn in a little bit. Now let's say that we pick a B of n, which is we're going to compare it to, but we found out that our original is actually greater than B of n. Well, that's fine, but B of n has to diverge. And if B of n diverges, then A of n also diverge. And the theory behind that is, well, let's say that our A of n is always going to be bigger than what we're comparing it to. Well, A of n is going real, let's say, to a certain number that we don't really know, infinity. Well, if we can prove that B of n is going to go to that value as well, and it's always going to be less than, which means that A of n is forced to diverge just because B of n is diverging as well. I consider this kind of like a trapping. If A of n is in the bottom, if B of n converges, it's going to get trapped in the middle. And the same thing here. If A of n is on top of B of n, if B of n keeps going up, then A of n is trapped to go also up as well. So, if you can compare these two and you can use these two, then it's a little bit easier to actually work with this. So we're going to do a couple of examples. Now, in our first example, we have the series from 1 to infinity of 1 over 3n to the 7th plus 9. Now, your main goal is to ask yourself, what can you compare it to? The reason why I know I can't use any of these series is because we've never dealt with a problem like this. So we have to compare it to something that's a little bit easier. Now, the one thing that we have worked with are exponents. So because of that, what I'm going to ask you to do is just compare it to something that you're used to working with. This right here. So we're going to say that, hey, well, I know that A of n is equal to 1 over 3n to the 7th plus 9. But let's just say that B of n is equal to 1 over 3n to the 7th. Now the next thing that you have to do is, okay, well, are they both positive terms? Well, yeah, because if you plug a number into here and plug a number into here, they're going to be positive. So, first statement, A of n and B of n are positive. So that checks out. Now the next thing is we have to determine is A of n less than B of n. And sometimes it's as easy as just looking at it. Let's say you plug in 1, our first term. That's going to be 1 over 3. But if you plug it into here, you're going to get 1 over 3, but then also you're going to add 9 to that 3, so now it becomes 1 over 12. Well, if you have 1 over 12, that's definitely less than 1 over 3. So because of that, we now figure out that A of n is less than B of n, which is nice. But remember, going back to that last page that we just worked on, if A of n is less than B of n, we have to prove that B of n is going to converge. So then what we're going to do is, okay, well, let's figure out what's happening with B of n. So n to 1 to infinity of 1 over 3n to the 7th. And then you have to ask, okay, what type of series is this? Well, the fact that there's an exponent 7, we know that this is a p-series. So this is going to be a p-series with p equaling to 7, which is nice because our next thing is that we're going to figure out, well, what happens when p is equal to 7? Is that going to converge or diverge? Well, because that's actually greater than 1, this is going to converge. So that means that our original will converge, and then you can say because of the comparison test. So in the case where A of n and B of n are positive, and we figure out that A of n is less than B of n, our B of n has to converge in order for us to use a comparison test, because that's what the theorem said before. If it doesn't, then we can't determine anything, and we have to use a different test. So always look to see what you can compare it to. The numbers that are being added or subtracted usually, what I consider kind of like the garbage rule. We're not going to compare it. We're not going to look at it. We're going to disregard it and only care about the stuff that we care about. Okay, so moving on to the next example. Look at it. Think about it. What are we working with? What could I compare this? If you think about the garbage rule, what you don't really care about is that -2, so just cover it up. Now you have 9n over 8n. The fact that the n is in the exponent should let you know that, hey, my A of n is going to be 9 to the n over 8 to the n, but my B of n is going to be everything except the stuff that's being added or subtracted, so that's 9n over 8n, but that's actually a geometric term because the n is in the exponent, which is nice because now you can figure out, okay, geometric, remember that's a ratio. What is your r? Is r greater than 1 or less than 1? But first thing you have to do is ask yourself, is A of n, B of n positive? It is. You plug a 1 into here, and any number, you're always going to get a positive number. So just state that A of n and B of n are positive. And the next thing you have to do is, okay, well, let's figure out what's happening with, is A of n less than B of n, or is A of n greater than B of n? Who knows? Well, if you plug a number into here, think about the rule. Remember, the fact that this number is being subtracted to this, whatever number this is going to be, this is always going to be less than that. And whenever you have a smaller denominator than the other one, this is actually going to be greater than. So A of n is actually greater than B of n. What that means is if you go back to the last slide, now B of n has to be divergent in order for us to work with something. Because B of n is always going to be less than A of n. So A of n is shooting up, B of n possibly is right underneath it. So we need to get B of n to be divergent. So let's figure that if it is. N equals 1 to infinity of 9 over 8 to the n. But remember, this is a geometric series. My r is equal to 9 over 8. Awesome. Because r is equal to 9 over 8, that's greater than 1, which means B of n is divergent. Therefore, since it fits it, I can now say from n equals to 1 to infinity of A of n, which is 9 to the n over 8n minus 2, is also divergent because of the comparison test. So remember, your goal is you're trying to compare it to something that looks similar to it. If it's something being added or subtracted, it's usually going to be disregarded, and it's whatever's over here. Now, the fact that n was in the exponent lets you know that that's going to be a geometric series. Also, whenever something is being subtracted to the denominator, your A of n is 9 out of 10 times going to be greater. But like in the old problem, the problem we just did, the fact that we were adding, A of n was less than. Look for those patterns. It's going to exist every single time. Now, our last thing that we're going to work on today is the limit comparison test. Now, the limit comparison test is only used when we go back to the original case that if A of n is less than B of n and B of n converges, then E of n of A of n also converge. If we find that A of n is less than B of n, but this diverges, this is not going to help us out. And because of that, we're going to now use the limit comparison test. And the same thing for the last case. If we find out that A of n is greater than B of n, and we prove that it converges by accident, B of n converges, we have to now use the limit comparison test. So the limit comparison test is used when the comparison test fails. So let's go ahead and do an example. If the limit comparison test, if the summation from A of n and B of n have positive terms, and the limit of A of n over what we're comparing it to, B of n, exists, meaning that it's a number, that it exists, it's a number, then both series will converge or diverge based off whatever you found of B of n. We have to remember one thing that I didn't say before. This is not going to give us a sum at all. Only thing that this is going to tell us is whether or not our series is convergent or divergent. Now remember, key thing, this is used when the comparison test fails. So let's go ahead and do an example. So they're going to ask me the same thing. I'm going to be given a problem, and I'm going to look at it, and I'm going to go, okay, I've never worked with a rational fraction like this that had a square root of n plus a number. So the fact that I see that plus or minus a number, I know that this is going to be a comparison test. So what I'm going to first do is, I'm going to say, okay, well, a of n is equal to the original, which is 1 over square root of n plus 1. So that means b of n is going to be equal to, remember, disregard this and only care about the front. So that's going to be 1 over n to the half. And the reason why I put the half should let you know, this is a p-series. So the next thing, are they positive terms? No matter what number I plug into here, a of n and b of n are going to be positive. So just note that a of n and b of n are positive. The next thing is, well, what's happening with a of n and what's happening with b of n? Is a of n less than or b of n greater than? Remember how I told you, whenever there's a plus, that means that this denominator is going to be a little bit bigger, which means that this fraction is going to be smaller than this fraction. So if a of n is going to be less than b of n. Now because of that, that's awesome, we're good. So now let's figure out, well, what's happening with b of n? What's happening to the summation from n equals 1 to infinity of our b of n? Well, remember how we said it was a p-series? Okay, this is a p-series. My p is equal to half. And then you have to remember the rules of p-series. The fact that this is less than or equal to 1, this means that my p-series, this b of n, is divergent. But, remember in the first case, if a of n is less than b of n, this has to be convergent. If this ends up being divergent, well, the comparison test is going to fail. So comparison test fails, which means that I don't know what's happening with a of n. I have no idea. So I'm going to go, okay, well, what's another way? Well, the other theory behind this is let's use the limit comparison test, which says, okay, well, they're both positive terms. Now let's find the limit as n approaches infinity of a of n over b of n. But that's just going to equal to limit as n approaches infinity of 1 over square root of n plus 1 over 1 over square root of n. Then you gotta keep change flip, because anytime you have a fraction, keep change flip it. And when you keep change flip it, you're going to get the limit as n approaches infinity of square root of n over square root of n plus 1. Now, the next thing that we have to work on once we have that is, well, let's go ahead and find a limit. When we plug infinity, we're going to get infinity over infinity, which doesn't help us out. It's an determinant. So let's figure out, okay, what else can we do? Well, the fact that every single thing has a square root of n, I'm going to divide everything by that. Which this is now going to give me limit as n approaches infinity of 1 over 1 plus 1 over square root of n. Plug infinity into here. I'm going to get 1 over 1 plus 1 over infinity, which is 0. This gives me 1. This is not telling me that this converges to 1 at all. Only thing that this tells me is that this limit exists. So because it exists, that means that, hey, I can now determine if this is convergent or divergent based off what I found out in my b of n. Why I said that b of n was divergent, and the fact that this exists lets me know that a of n is also divergent because of the limit comparison test. So once again, the limit comparison test is only used when the comparison test fails. When it fails, we're going to say, okay, well, let's just take the limit of a of n over what we're comparing it to, keep, change, flip, do a little bit of algebra, and find the limit. Once you find the limit and it gives you a number, that meaning it exists, then we can go ahead and say that a of n is going to converge or diverge based off what we said b of n happens before. Okay, so remember, the limit comparison test is only used when the comparison test fails. Alright guys, thank you for watching. I hope it helped, and let me know how this went.